My dear student, today let us talk about non-measurable sets. So far we have discussed about the measurable sets and measurable functions. So if there is measurable set, then we want to know, is there non-measurable set or not? Okay, so today's lecture is all about finding an example of non-measurable set. So before doing that, we are going to establish a small result. The result is this theorem. So E is a measurable set. So this E is a measurable set. Okay, E is a measurable set. Then for its Y, we define the E plus Y, a new set defined by X plus Y such that X belongs to E. That means the set E is translated by an amount of Y, E plus Y. Okay, is a measurable, and the measure of E and the measure of E plus Y are equal. Okay, they are equal. Let us this result we have done for any set. Means we have last time we discussed about this. So M star for general set M star of A is equal to M star of A plus X. We have done this result. The outer measure of a set A is exactly equal to outer measure M star of A plus X. So outer measure is translation invariant. So we have done this one. So if A is measurable and if A plus X is also measurable, then this star will be dropped. M of A is equal to M of A plus X. Okay, so in case of measurability we use the symbol E. Okay, so that means M of E is equal to M of E plus say Y. Let us say Y in our theorem. Okay, so this equation you can write when you know that E plus Y is measurable. Alright, so E is measurable, then E plus Y is also measurable. But this one for outer measure case, this is true. This is always true. Whether this A is measurable or not doesn't matter. Outer measure of a set A is equal to outer measure of A plus X. Okay, so if E is measurable, here star is dropped, but we don't know E plus Y whether it is measurable or not. Okay, so we are going to prove that if E is measurable and then E plus Y is also measurable, okay, then we can drop star here. That is, we want to establish this result. You might feel that this result is redundant to this one. Okay, but we haven't proved that if A is measurable, A plus X is also measurable. We haven't proved that one. Okay, so we need to prove that E plus Y is measurable, then this result is established. Okay, so that is all about. Then let us go back to the theorem of regular measure theorem. In the regular measure theorem, what we say is that says this set, this is E, this will be measurable if and only if for a given epsilon. This set is measurable if and only if for a given epsilon there exists an open set O, which is a superset of E, such that measure of or outer measure or measure. Okay, so we'll drop outer measure here. Measure of O difference E is less than or equal to epsilon. All right, so this is the measurability condition. All right, so let me repeat again. A set E is measurable if and only if for a given epsilon there exists an open set O containing the set E such that this inequality holds true. Okay, then we say that this set E is measurable. We are going to apply this theorem in proving that E plus Y is measurable. Suppose, let us draw one diagram again. Suppose this is your set of real number, a real line. Suppose this one is this one is your O. This is your O, and somewhere here it is E. So this is E. So this inner set is E, and this whole is O. O is open set. Okay, so O is a superset of E, means E is inside O, like this. Okay, then how does it look like E plus Y? So for every element here you add Y, then it will be translated here. Suppose it is here. All right, this is this set is what? This will be E plus Y. So if this is E, then E plus Y will be this one. Right, E plus Y. Then what about, sorry, this will be O plus Y. O plus Y. So if this is O, then O plus Y will be this. Then what about the E plus Y? E plus Y will be here again. E plus Y will be here. So this inside set is E plus Y, and this is O plus Y. So the set of real number is a topological group. So if O is open, O plus Y is also open. Right, so from the figure it is very clear that O plus Y is a superset of what? E plus Y. All right, O plus Y is a superset of E plus Y. Then what about this difference? O plus Y, this is a set, another, this is a set, then difference E plus Y, this set. So what is this set? This is set what? According to set difference definition, this is your O plus Y. From here to here it is your O plus Y. All right, this is your O plus Y. From that you take out E plus Y, the remaining set of point here. Okay, this will be what? Your difference set. So that is also, what about O plus E? O plus E will be here. O minus E will be here, or O difference E will be here. So these are the O difference E. Means from O you take out E, the remaining set is O difference E. So if a point here you take out from O difference E, if you add Y, then it will be here. All right, then it will be here. So if you take one point from here and then you add, then it will be here. That means what? O plus Y difference E plus Y is exactly equal to O difference E plus Y. O difference E plus Y. All right, so O plus Y difference E plus Y is equal to how much? O difference E plus Y. All right, so again your E plus Y is a it is a subset of what? O plus y, and O plus y I already explained you. O plus y is open set containing E plus y. So these are the background, then the theorem will be easy. Okay, so what do we want to show? We want to show that for every measurable set E and for every real number y, E plus y is measurable. Okay, then measure of E is equal to measure of E plus y. That is what we want to show, and that is all about the theorem. Okay, so let us see here. Now E is a measurable set for its y. New set E plus y is also measurable, and its measure is equal to the measure of the set E. So what we are given is that E is measurable. Okay, so according to that regular measure theorem, for a given epsilon, if E is measurable for a given epsilon, there must be an open set containing open set O, open set O containing E such that measure of O difference E is less than or equal to epsilon. Alright, is less than or equal to epsilon. This must be true if E is measurable. For any given epsilon, this must be true. We should be able to find a suitable open set O containing E satisfying this condition. This must be true if E is measurable. Okay. So then I already explained you O plus E. O plus y is an open set. E plus y we don't know. Here this R is. Okay, this is a mistake. This is not R. O plus y is an open set containing E plus y. It should be like that. O plus y is an open set containing E plus y. Alright. So then O plus y difference E plus y is equal to O difference E plus y. I already explained you now. So this is obvious. O plus y difference E plus y is equal to O difference E plus y. Okay, and then let us see. So then let us see. Here I drop m star because ultimately E plus y is going to be measurable. Okay, so O plus y difference E plus y is equal to, because of equality of this set, measure of O difference E plus y. So this is equal, again here also I drop m star. This is equal to what? M O difference E, but M O difference E is less than epsilon. From here it is less than or equal to epsilon, then this is less than or equal to epsilon. So let us just forget about this. Let us just see at first one and the last one. What does it say? We are able to find an open set O plus y containing E plus y such that measure of this difference set is less than or equal to epsilon. This is true for any given epsilon. So what does it say? It says that measure of E plus y is measurable. Okay, E plus y is measurable. Let me explain again why we say that E plus y is measurable. For a given epsilon, okay, we are able to find an open set O plus y containing E plus y such that measure of this difference set is less than or equal to epsilon. So because of this, we can say that E plus y is measurable. So E plus y is measurable. It follows that E plus y is measurable since outer measure is translation invariant. Okay, since outer measure is translation invariant. So I told you here I drop m star. Okay, we have m star E is equal to m star E plus y, but this being measurable and E also measurable, m star E is equal to me is equal to m E plus y. So this completes the proof. Okay, so what is the thing you have to remember? If a set E is measurable, the new set defined E plus y, okay, is also a measurable set, and measure of E is exactly equal to measure of E plus y. Alright, so this is the small theorem. This is going to be used in our proof, proof of a non-measurable set, existence of a non-measurable set. So let us see this theorem. There exists a non-measurable set. There exists a non-measurable set. Yeah, we have talked about so many measurable sets, measurable function, but we haven't talked about any non-measurable set. So this is the first time we are talking about non-measurable set. we want to establish an example, okay, of a non-measurable set. Yeah, let us talk about first the 0, 1 closed interval. 0, 1 closed interval, and then define on this set a relation. Okay, a relation. Let us define a relation. It is defined by this one: x is related to y. Okay, for two member x, y in 0, 1 closed interval, we define a relation, and x is related to y if and only if the difference y minus x is a member of this set, means it is a rational number between -1 and 1. Okay, if y minus x is a rational number between -1 and 1, okay, then we say that x is related to y. All right, so this is an equivalence relation. You can easily establish. You do it as an exercise, as a homework. So I am not giving you the proof here, but you can do it easily. You just prove that this is an equivalence relation. Okay, it can be easily verified that the relation is an equivalence relation on 0, 1 closed interval. So what is the relation? Let me explain again. Two member x, y in 0, 1 closed interval, they are related by this relation. They are related to each other if and only if the difference y minus x is a rational number between -1 and 1. Okay, q intersection -1 1, q is a set of rational number, intersection -1 1 is a set of rational number between -1 and 1. Okay, if y minus x is a rational number between -1 and 1, then we say that x is related to y. If x is related to y, then y minus x must be a rational number between -1 and 1. Okay, so this is the definition of the relation, and this relation is an equivalence relation. So you can prove it easily. It is an exercise for you. You can do it. Okay, so if you are able to do that one, you will understand. Okay, you will understand more. Okay, so you try it. So it is an equivalence relation on 0, 1 closed interval. Okay, then by that theorem, fundamental theorem of equivalence relation, so the set 0, 1 closed interval can be partitioned into equivalent classes. Okay, means this set 0, 1 closed interval can be expressed as a disjoint union of equivalent classes. E alpha are equivalent classes. Okay, so alpha belonging to capital lambda, alpha belonging to capital lambda, so disjoint union. Okay, so E alpha and alpha beta is a member of this one. E beta is also there. E alpha intersection E beta, they are empty set. Okay, disjoint union, where E alpha are disjoint equivalent classes. Okay, they are disjoint equivalent classes. So equivalent class means what? If x and y are member of E alpha, then x is related to y. Okay, so whatever point related to x will be in E alpha. Okay, x, y belong to E alpha implies and implied by, so this should be y minus x. So there was a mistake. Y minus x must be a rational number q1. What is q1? Q1 is equal to this set. Q1 is this set. The set of rational number between -1 and 1 is denoted by q1. Okay, so E alpha. So suppose you have another E beta is also there, then take 1 point from E alpha and 1 point from E beta. They are not related. Okay, they are not related. So if x and y are member of E alpha, then x is related to y according to the relation. All right, so that is the definition of equivalent classes, equivalent class. So 0, 1 is disjoint union of such equivalent classes. Then let us see. You already know that the set of rational number is countable. The set of rational number between -1 and 1 is also countable. The set of rational number q1 is countable. So again, you know, from this you can easily conclude that E alpha is a countable set. Okay, E alpha is a countable set because of this one. Y minus x belongs to q1. Okay, so whenever you take 2 points x, y in E alpha, their difference is going to be a member of q1. So q1 being countable, E alpha is also countable. So E alphas are all countable sets. is E alpha is a countable set, but so 0 1 closed interval is not a countable set, but 0 1 closed interval is expressible as a disjoint union of these E alphas, where each E alphas are countable. So if this is a countable union, means if capital lambda is a countable set, this is going to be a countable union of countable sets, then ultimately what, 0 1 closed interval is going to be countable. That is not going to happen. So what is the thing then? Even though E alpha is countable, but this union is not going to be a countable union. Okay, this is not a countable. So then there are uncountably many E alphas. Each E alpha is countable, but such type of E alpha are so many are there, they are not countable. Okay, okay, the number of E alphas are not countable. The set E alpha is countable, but E alpha, E beta, so many such sets are there, they are not countable. Okay, so there are uncountably many such E alphas. There are so uncountably many such E alpha. That means this index is uncountable. Okay, this index is uncountable. So what is the point? E alpha is countable. Is E alpha is countable, so, but such number of sets are uncountable. Okay, then there are so many E alpha. Okay, there are uncountably many E alphas. Then now let us define a new set V, which is a subset of 0 1 closed interval. Let us define a new set V, which is a subset of 0 1 closed interval. How we define? From each E alpha you just take randomly 1 point. Okay, only 1 point, just 1 point from E alpha. Okay, from E beta also you take 1 point. From so many E alpha are there, from these E alphas you take 1 point, just 1 point. Okay, and then form the new set V. So what is V? V is containing just one element from just one element X alpha from E alpha. All right, you take one point from each E alpha and form a set, and that set is called, let us call it V, and it is a subset of 0 1 closed interval. Then what happened? Since you are taking just 1 point from each E alpha, and E alpha is, you know, how many such E alpha are there? There are uncountably many E alpha. Then B is also uncountable. Okay, B is uncountable. All right, B is uncountable. Okay, so then, you know, the set of rational number is countable. So the set of rational number in the -1 closed interval can be enumerated into a sequence like this, Ri B. So let Ri be an enumeration of the rational number Q1, and define Bn. Then let us define Bn. For each n greater than or equal to 1, for each natural number n, let us define the new set Vn. How we define? Bn is equal to V plus Rn. You take one rational number from here, you sum to the set V, then you will get the set Vn. All right, so let us, you know, let us see about the construction of V here. You know, let me go back to the window. See, you have so many E alpha, you know, say you have E alpha, you have E beta, you have gamma, like this. Okay, so alpha beta gamma is from the index set capital lambda. So from here you take randomly 1 point X alpha, from here you take 1 point X beta, like this. From here also it has countably many elements, it has also countably many elements, it has countable element, but such set they are uncountable. So how many such sets are there? So many sets are there, they are not countable. Okay, so you take 1 point X alpha from here, so like this it is, you go on like this. So this set is what? This is your V. Okay, from each E alpha you take 1 point and form the set V like this. All right, so then let me ask you one question. Does X alpha related to E beta, X beta? No. x alpha is not related to x beta. You know, this is equivalent class. So only member inside E alpha, they are related to each other. A member from E alpha is not related to a member of E beta. Okay, a member of E beta is not related to a member of E gamma. So these are the equivalent class, disjoint equivalent class. So relation is maintained inside E alpha only. That is what we call it equivalent class. Relation is maintained here inside E beta, E gamma, like this. Okay. And then how you define Bn? Let us see. This is your B. Then for each natural number n, then there will be, you know, this the set of rational number q1 is equal to how much? This is Ri. You can enumerate like this: R1, R2, R3, R4. R1 is not equal to. They are all distinct. Okay, they are all distinct. R1, R2, R3. Lord, since it is countable, you can write it like this. You can make an enumeration of q1, and that enumeration is, let us call it Ri. Okay. So for this natural number n, there will be Rn. Okay, then you add to Brn. You add, okay, to add B to Rn. Then the new set is Bn. All right, the new set Bn is defined like this. So similarly, you can define B1, B2, B3, B4, B5, B6, goes on like that. Okay, then so what? This new set, collection of set B1, B2, B3, they are a countable set. B1, B2, B3, B4, there you have a collection of countable sets. Okay, they are a countable set. Now let us prove that they are disjoint also. Pairwise disjoint means B5 and B4 are disjoint. No, there is no common point between B5 and B4, like that B3, B4, like the B3 and B5. There is no common point. They are pairwise disjoint. Okay, so let us prove that one. Right. So up to this, now what we have done, we have defined V, we have defined a relation, then we define the equivalent classes. Okay, and then we define the we give an enumeration of the set of rational number in -1, 1 closed interval. Then ultimately we have defined Vn. We have defined Vn. So you have to see each step very carefully. Okay, now let us claim, first claim. Let us see Bn intersection, you know, Bn intersection Bm is equal to phi if n is not equal to m. Okay, if n is not equal to m, they are disjoint. They are disjoint means what? This sequence of set B1, B2, they are pairwise disjoint. Okay, they are pairwise disjoint. This new sequence of set B1, B2, B3, they are pairwise disjoint. Okay, let us prove that one. So if possible, let us assume that they are not disjoint. If they are not disjoint, means they are non-empty, then there will be one element, common element. Y is a member. Suppose if possible, let us take one more point y in the intersection Bn plus Bm, means y is a member of Bn, y is also a member of Bm. Okay, if possible, let us assume that Bn intersection Bm is non-empty. That means there will be one element. That element let us call y. Y is a member of Bn, it is also a member of Bm. Okay, so then y is a member of Bn means, according to the definition of Bn, how we define Bn. Okay, y is a member of Bn means what? Y is a member of Bn means y must be equal to some element of B plus some rational number. Okay, suppose that element of B, let us call it x alpha, and suppose that element of Ri, let us call it Rn. Okay, so that is the concept. So you know, so y is a member of Bn, it is also a member of Bm, means there are element x alpha and x y beta in B such that, you know, such that y is equal to x alpha plus Rn. Okay, y is member of Bn means what? Y must be expressible as a sum of some member x alpha in B plus some member Rn in the rational number q1. Again, y is also member of Bm means y must be expressible as a sum of some member y beta in Bm. This y beta is in Bm. Okay, plus some rational number Rm from the q1. Okay, from q1. All right, that means since y is equal to y is equal to this y, they are equal. That means x alpha plus Rn must be equal to Rm, okay, plus y beta. So then ultimately you will get x beta minus x alpha is equal to Rn minus Rm. Difference of two rational number is again a rational number, and you can easily check that rational number is a member of Q1. That rational number is a Q1. Okay, so from here what happened? Okay, let us see. X beta, how you take x beta? X beta you take from E alpha or E beta, and x alpha, how you take x alpha? X alpha you take from E alpha. So x beta is from E beta, x alpha is from E alpha, but E alpha and E beta, they are disjoint. Okay, they are disjoint. So the only thing is that beta must be equal to alpha. That means E beta is equal to E alpha from the definition of V. Okay, from the definition of V. So because why? X beta difference x alpha is equal to rational number. This means that what? X alpha is related to x beta. So since you took x alpha from E alpha, x beta from E beta, they cannot be related to each other. There cannot be any relationship between x beta and x alpha. Okay, the only thing is that x beta must be also from the same set. Okay, x alpha. Okay, x alpha and x beta must be from the same set, means since you take one element from each set, they must be equal. X beta is equal to x alpha. All right, so let me explain again. From this you get what? X beta minus x alpha is equal to Rn minus Rm, but Rn minus Rm, this is a rational number and it is a member of Q1 also. So x beta minus x alpha is a rational number. That means what? X alpha is related to x beta, but x alpha is coming from E alpha, x beta is coming from E beta. So a member coming from E alpha cannot be related to a member coming from E beta. The only possibility is that they must be coming from the same set. Okay, if there is a relationship between x alpha and x beta, these two, x alpha and x beta, must be coming from same set E alpha. Okay, if they are coming from the same set E alpha, then x alpha must be equal to x beta. Okay, by definition of B. All right, so if x beta is equal to x alpha, what do you get? This is 0. Then Rn minus Rm is equal to 0, means Rn is equal to Rm. But this is a sequence of distinct rational number, so they are equal, means what? N is equal to M. So this is a contradiction. Okay, but you are having here N is not equal to M, but your conclusion is like that N is equal to M. So this conclusion comes from our wrong assumption that Bn intersection Bm is non-empty. Okay, so it should be empty. That means the sequence of set B1, B2, B3, they are pairwise disjoint. Okay, Bn, so what is the conclusion? Bn intersection Bm is equal to phi if n is not equal to m. So this sequence of set B1, B2, B3 up to infinity, it is a sequence of pairwise disjoint sequence of sets. Okay, and they are subset of 0, 1 closed interval. All right, so this, so far we have this result. So next, let us take one arbitrary point from 0, 1 closed interval. X be a point from the 0, 1 closed interval. Then what? 0, 1 closed interval is equal to how much? It is equal to union of E alpha. So X must be member of some E alpha. Okay, because in the earlier one, 0, 1 is equal to how much? 0, 1 is equal to this much. Okay, union of this disjoint sets. So if you take one member from here, then that member must be in some E alpha. Okay, in some E alpha. So then X is a member of E alpha for some alpha. That means what? For X alpha belongs to E alpha, and you take another X, X is from E alpha, and then you take another member X alpha from E alpha, then X and X alpha are in they are in E alpha, then they must be related. That means what? Their difference is a rational number. Okay, that means what? By the definition of relation, both x and x alpha are in E alpha, therefore they are related. They are related to each other. That means what? X minus x alpha is a rational number. It is a rational number in -1 1, so it must be equal to for some Rn, because the set of rational number has been enumerated by R1 R2 like this. Okay, so it must be equal to Rn, say for some Rn. All right, so from here what do you get? X is equal to how much? X is equal to x alpha plus Rn, but x alpha plus Rn is a member of Vn. No? By our construction of Vn, x alpha from V plus Rn, rational number, it is a member of Vn. Okay, so that means what? Well, whenever you take one arbitrary point x from this closed interval 0 1, that point is also a member of Vn. That point is also a member of Vn. That means what? This 0 1 closed interval, this 0 1 closed interval is a subset of this countable union. Any member here is a member of some member here. Okay, that is union, and going from 1 to infinity Vn, 0 1 closed interval is a subset of this. All right, so this you know it. We are coming to the conclusion very nearly. So next, let us see. Let us take an arbitrary point from Vn. By our definition of Vn, this x must be expressible as a sum of x alpha Rn. Okay, for some alpha, where x alpha is a member of 0 1 closed interval. That means x alpha is bounded by 0 and 1. And what about Rn? Rn is a rational number between -1 and 1, so Rn is bounded by -1 and 1 like this. So if you add together, what happens? X alpha plus Rn is bounded by 2 and -1. Okay, so their sum is called x. No, so x is bounded by 2 and -1. What does it say? Whenever you take one point from here, that is always bounded by 2 and -1. Okay, lower bound is -1, upper bound is 2. That means what? This union is a subset of -1 2 closed interval. Okay, this union, it is a subset of -1 2 closed interval. All right, so combining this inclusion and this inclusion, ultimately you get this inclusion. Okay, 0 1 closed interval is a subset of union n going from 1 to infinity Vn, which is a subset of -1 2 closed interval. Okay, so this is the crux of the problem. All right, we are able to construct Vn, and we are able to show this inclusion. Okay, this inclusion, we are able to show this inclusion. So then, if V is measurable, just before doing this theorem, we just prove one small result. If V is measurable, what happened? By that theorem, V plus Rn is also measurable for every real number. So Rn is a real number. If V is measurable, V plus Rn is measurable, and measure of V plus Rn is exactly equal to Vn. All right, measure of Vn, that is measure of V plus Rn, is exactly equal to measure of V. All right, so this is the thing we have. So if V is measurable, what happened? Vn, that is V plus Rn, is also measurable for each n. For each n, for n is equal to 1, you have V1. If V is measurable, V1 is also measurable, and the measure of V1 is equal to measure of V. For n is equal to 2, you have V2. V2 is equal to V plus R2. V is measurable, therefore V2 is also measurable. Measure of V2 is equal to measure of V, like this. It goes on like this. So measure of Vn is equal to measure of V for every n greater than or equal to 1. For every natural number n, measure of Vn is equal to measure of V. So this is the idea we have so far. Then what happened? From measure theory, this set is a subset of this, and this is a countable union, disjoint countable union. So measure of this one is equal to measure of the sum of the measure of Vn. So measure of Vn plus measure of V2, like this, it goes on. And this is a subset of this one. So measure of that set is a subset, it is less than or equal to measure of this one. So from measure theory, that we have. Therefore measure of 0 1 closed interval, it is actually equal to 1, is less than equal to summation n going from 1 to infinity mvn, but this summation is equal to what? mv1 is equal to mv, mv2 is equal to mv, like that. No? So that measure of v, how many times you add up together? You add up to infinitely many times. So their sum is less than equal to 3. Okay, measure of minus 1 2, that is 3. Okay, so that means what? 1 is less than equal to, you know, measure of v dot infinity, and this is less than 3. So is this possible? If measure of v is not 0, then measure of v into infinity is going to be infinity, then infinity is going to be less than 3. That is not possible. So measure of v is not going to be a non-measure, non-negative or non-zero. Okay, measure of v cannot be non-zero. Okay, if it is non-zero, measure of v into infinity is going to be infinity. Infinity cannot be less than 3. All right, that is wrong. That cannot be true. All right, so if measure of v is equal to 0, what happen again? So according to our definition of extended real number in measure theory, measure of v, if measure of v is 0 into infinity is 0 in our extended real number in measure theory. So this is going to be 0, and 0 is going to be greater than 1. That is also not possible. So in all possibility, you are getting a wrong inequality. This is not possible. So why does this happen? This happen because measure of v is not measurable. Okay, so whenever you assume that v is measurable, you are in a situation which is not acceptable. Okay, you are in a situation which is not mathematically acceptable. Okay, because infinity, if measure of v, if v is measurable, it should be something either 0 or some non-zero real number. So in that situation, measure of v into infinity is going to be infinity, and it is going to be less than 3. That is not acceptable. Okay, and if v is measurable, suppose measure of v is 0, then 0 into infinity is 0, and that is going to be greater than 1. That is also not acceptable. So in all possible cases, you are in a situation which is not acceptable. Okay, which is not acceptable. So this situation arises from our assumption that b is measurable. Okay, b is measurable, so b should not be measurable. B should not be measurable. So now we are able to construct a set which is not measurable. How we construct the set? It is a very, very lengthy step. So many steps, so many things. So this is the thing. So you study it, you watch it, and you can copy the note also. Wherever I make correction, you can correct it, and then you can talk to me also through phone. Okay, this much I want to give today. Thank you.